One bad BGP decision can black hole traffic, send packets the wrong way, or leak routes far beyond a single router. In this deep dive, you'll learn how paths are chosen, how policy bends those choices, and how to troubleshoot the whole chain. Inside your network, an IGP like OSPF or EBGP helps routers find paths within one administrative domain. BGP solves a different problem. It lets separate networks exchange reachability across autonomous systems. Think of a company connected to two ISPs. Your routers aren't asking which path is shortest in hops alone. They're asking which prefixes are reachable, through which provider, and under what policy. That's the mental shift that makes BGP click. BGP is reachability plus policy. If you miss the policy part, the rest feels random. At its core, BGP is a path vector protocol. A neighbor advertised NLRI, which is the reachability information for prefixes, along with attributes that describe how that route was learned and how it should be treated. Those neighbors don't shout routes into the air. They build a TCP session on port 179, exchange updates, and then mostly send changes instead of resending the whole table every time. That's why incremental updates matter so much. Once the session is up, BGP keeps the control plane efficient by advertising what changed, not starting from zero. When peers sit in different autonomous systems, that's EBGP. When they stay inside the same AS, that's IBGP. Same protocol family, very different design and policy implications. Now let's make peering practical. Direct EBGP is the simplest case. Two edge routers connect, each side defines the neighbor and remote AS, and the session comes up over that directly connected link. IBGP often looks different. Engineers peer to loopbacks for stability, then use update source so the session forms from the loopback address instead of a physical interface that might change. As soon as peers are not directly connected, multi-hop and underlying reachability matter. If the loopbacks can't reach each other through the IGP, BGP never gets a chance to work. That is why so many BGP failures are really IP connectivity failures wearing a BGP mask. You do not need the finite state machine as trivia. You need it as a map. Idle means the process is waiting to start. Connect and active usually point you back toward TCP reachability and session setup. Once TCP succeeds, BGP sends an open message. If the parameters make sense, the peers trade keep alives and move through open sent and open confirm toward established. Update messages carry route changes. Notification messages end the conversation when something is wrong, like a bad capability, a malformed update, or an authentication mismatch. Timers matter too. If keep alives stop or hold timers expire, the session drops. That tells you the problem may be loss, instability, or a control plane path that isn't staying healthy. Attributes are where BGP stops being a directory of routes and becomes a control system. They carry the clues and policy signals that shape which path wins. Next_hop tells the router where to send traffic next, and if that next hop isn't reachable, the route can fail before best path selection even gets interesting. As _path shows which autonomous systems the route crossed and helps with loop prevention and path preference. Inside an AS, local preference is a big lever because it tells your routers which exit they should prefer. Weight is even more local. It matters only on the router where you set it, which is why it's useful but not portable thinking. Origin and med show up deeper in the comparison, but they still matter in close contests. Med is often used to hint which entry point a neighboring AS should prefer, though only under specific comparison conditions. Communities are the scalable language of policy. Instead of writing one-off rules everywhere, you tag routes once and let providers or internal routers act on those tags consistently. If you remember one thing here, remember this. Attributes are not decoration. They are the inputs that drive control, scale, and troubleshooting. Now we get to the heart of BGP. Imagine an enterprise learns the same prefix from two ISPs. The router doesn't just pick one at random, it walks a decision process. First, the route has to be valid, and the next hop has to be reachable. A path with a dead next hop should not win, no matter how attractive its attributes look on paper. Then come the high-impact attributes. Highest weight wins on that router. Highest local preference wins across the AS. Locally originated routes can also beat learned ones in the right context. If those are equal, the router keeps comparing. Shorter AS_path is preferred, then better origin, then lower med when that comparison applies. This is where a provider's signal can start to matter. After that, BGP often prefers EBGP over IBGP, then looks at IGP cost to the next hop and finally falls into tiebreakers. So the winner may reflect both policy and underlay design, not just one clever knob. This is the operational payoff. When the wrong path wins, you can stop guessing and walk the decision chain until you find the exact reason. At the edge, EBGP connects you to other autonomous systems. Inside your AS, IBGP spreads those external routes internally. That split is simple in a small lab and much more interesting in a real network. Pure IBGP full mesh does not scale well because every router needs a session to every other router. Route reflectors reduce that explosion, but they also change how routes propagate and can hide design mistakes. Confederations are another scaling tool. They break a large AS into sub-autonomous systems internally, while still presenting a unified face outside. You won't use them everywhere, but you should know why they exist. Next hop self is one of those small commands with huge consequences. Without it, internal routers may learn a route but still fail to use it because the external next hop is not reachable the way you assumed. If best path selection is the engine, policy is the steering wheel. This is where engineers stop observing BGP and start shaping outcomes. For outbound control, local preference is usually the star. An enterprise with two ISPs can prefer one provider for SAS traffic and another for backup or lower priority exit paths. For inbound influence, you have less direct control, so you use tools like AS_path prepending and sometimes MED. You're not commanding the internet. You're nudging how other networks may choose to enter yours. Filtering is non-negotiable. Prefix lists and route maps decide what you accept, what you advertise, and what gets modified on the way through. Without them, accidental route leaks become much easier. Communities make policy scalable across many prefixes and neighbors. Tag a class of routes once, then let downstream policy act on that meaning instead of repeating the same logic everywhere. The big lesson is simple. Strong BGP policy is deliberate, layered, and defensive. It chooses paths on purpose and prevents routes from escaping where they never should have gone. Good BGP configuration is not a bag of commands. It is a workflow. Start with your local AS, define each neighbor, and make sure the remote AS matches the relationship you actually intend to build. Then decide how routes enter BGP. You might originate a network directly, redistribute carefully, or inject routes through policy. Each option changes what you advertise and how much risk you carry. After that, come design-specific commands like update source for loopback peering, EBGP multi-hop for non-direct peers, and next hop self so internal routers can actually use what they learn. Finally, attach policy on purpose. If you cannot explain why a route map, prefix list, or community rule exists, it probably does not belong in production yet. Verification works best as a sequence, not a panic search. Start with the summary view. Are neighbors up, and how many prefixes are you actually receiving or sending? Then drill into neighbor details and the BGP table. Check capabilities, timers, message counters, learn paths, and whether the route you expect is even present in BGP at all. Next, compare the BGP table to the routing table. A route can exist in BGP and still fail to install because the next hop is unreachable, a better route won, or policy blocked it. Finish by checking advertised and received routes plus policy effect. That tells you whether the problem is what you learned, what you selected, or what you chose to export. When BGP breaks, troubleshoot in layers. Start with plain IP connectivity. Can the source address reach the neighbor at all? If not, BGP is not your first problem. Then validate the neighbor definition itself. Wrong remote AS, wrong update source, missing multi-hop, bad authentication, or a loopback that is not reachable will stop the session before routes ever matter. If the session is up but routes are missing, check origination and filtering. Maybe the prefix was never injected, maybe a prefix list blocked it, or maybe a community triggered a policy outcome you forgot about. If the route is present but traffic still breaks, inspect next hop reachability, route reflection behavior, and the best path chain. Many hard case are really selection problems, not peering problems. That layered workflow is what separates random command entry from real BGP troubleshooting. Here's the model to keep. Build the session. Exchange reachability. Compare attributes. Pick the best path. Install the route. Apply policy. When you can trace those steps, BGP stops feeling mysterious. And that is why BGP failures can hit hard at scale, but they are also diagnosable. When you understand the chain, you can reason through the failure instead of memorizing symptoms.